lecture 22. I noticed that you all heard the scary music and all my little fuzzy mole students at the bottom started shaking with excitement or fear for the fact that it's lecture 22 on the stereochemistry of E2 reactions. So a little review from last time and last lecture, but a little more detail for this lecture. Okay? So I hope you enjoy it. Let's take a peek. This was the last slide that we finished our last lecture on. So I just want to review this for us and make sure we're clear about this, is that an E2 elimination occurs with a strong base and a leaving group, and that there are two possible ways that we could do this elimination. But what seemed to be coming up in a lot of questions were, wait a second, I have a strong base, or is it a nucleophile? How do I tell the difference between the two? So I'd like to show you a slide that'll go into that detail. So is it a strong base, good nucleophile, E2, SN2? How are you going to know? So hopefully this slide will give you that information. SN2 reactions are favored by good nucleophiles that are not very good bases. So they can't do elimination. Aprotic solvents, again, favor this SN2E2 process. I thought I'd just throw that in there, but it's just a little thing. So here are our most likely good nucleophiles that are weak bases. So you'll notice the CN minus, the acetate ion, and so that's what this one here is trying to show. This structure here is what that one is. And you can see it's not a very strong base due to resonance of that O minus. But being negatively charged, even that resonance allows for it to still be a good nucleophile. So this will still be an SN2 nucleophile, which is really cool. Okay? And it doesn't have to be just a methyl group. You could have anything besides the CH3. You could put an R group of any size. So this will be a good nucleophile. All right? What are E2 then is everybody else that is negatively charged, typically are very strong bases. So here are some small bases that we're familiar with. And again, notice the small print on this one. This one will do E2 on everything but primary leaving groups. Because the primary aliphatic, for example, it's small enough, not sterically hindered enough, that these strong bases will still do an SN2 reaction. So be on the lookout for sodium hydroxide, sodium ethoxide, or any of these alkoxides. And they don't always have to be sodium, they could be potassium salts. Again, these are just spectator ions. Please ignore them. Don't let them get into your subconscious and distract you. Okay? So E2 is favored by these small, little, strong bases. If we get these big, bulky bases, and there's only two that I've given you so far, and really only one that you need to keep in your head. One, this T-butoxide can be written in this form. It can be written sodium T-butoxide, or LDA is a separate second one. It's also big and bulky. But this T-butoxide here is too big. It will always do E2. So if you want to ensure that even if you have a primary aliphatic, any kind of leaving group on a molecule, and you want to make it go E2 no matter what, you use this big bulky base. Okay? And that's the story of E2 versus SN2. And how to tell the difference between a good nucleophile and a strong base. Lastly, I'd be remiss if I didn't show you what you need for SN1. SN1 means that you've gone through this process and looked through the SN2E2 categories and realized, wait, I don't have a good nucleophile. I don't even have a good base. I have, say, the conjugate acid of a good base, like water. or ethanol, otherwise written as E2ETOH sometimes. You'll see that. So these are very, they're not bases at all. These are neutral molecules. And therefore, they can't do SN2 or E2. And so the only thing they're able to do is SN1. Okay? Helping this SN1 process happen more would be if you use these nucleophiles, poor nucleophiles. They are protic. Go ahead and use them as your solvent as well. 2 for 1, solvent and nucleophile. That would make a great SN1 reaction. Okay, so let's get back to our stereochemistry of the E2 reaction now that we know what these bases are all about. And what I want you to gather from this slide is that there really are 2 ways that you could actually have your E2 process. So in review, I don't know if you can see it here, but here is my hydrogen and leaving group. Let's make sure they're clear. Hydrogen and leaving group attached to, say, 2 bonds next to each other. Not on the same atom, but one right next to the other. And this molecule can spin. It's all single bonded. All right? So to make that pi bond again, I can spin it around until they obtain the orientation on the top here where the hydrogen and the leaving group are on opposite sides, and they are planar to each other and trans or anti to each other. Does everybody see that? It's kind of cool. Feel free to break out your models. If I have it in this orientation, then a strong base can come along as B minus and start taking off this proton on the beta carbon. And the pair of electrons here would then fold in and make a nice double bond. But that means you'd have to lose your leaving group. Would have to pop off as well. Okay? And this is one way. And again, you would make this alkene, and it looks like it would be the exact same alkene as if this molecule flipped a little bit and rotated and got the leaving group and the hydrogen on the same side next to each other, and the base came and grabbed the proton here and made a double bond by ripping this leaving group off. Would have to take this pair of electrons and leave. So as long as these p orbitals are aligned, you have a beautiful alkene double bond. But in this slide, both alkenes that are shown here in this slide, both of these are the same molecule. So it seems like, what's the big deal? Nick, I could make the alkene the same alkene. Either way, it doesn't even matter. What's going on? What if these were not all hydrogens attached? But what if these were different functional groups? What if this was, instead of a hydrogen, say, a benzene ring? And this one was, say, another benzene ring? Then would these be the same molecule? Could I create different alkenes? And that's what I'd like us to look at next. And if these two were to form, would one of these be favored over another? So let's go play. So if you were to align the hydrogen away from the leaving group, or otherwise known as anti, okay? Notice it has this beautiful orientation of the hydrogen and the leaving group being anti to each other. Notice if you do that with this alkane chain, what do you form? What do we call this type of conformation where they're anti to each other and nobody's overlapping bond-wise, atom-wise? Yep, you guessed it, staggered. Woohoo! We love staggered. So if you get the hydrogen and the leaving group anti to each other, one up, one down, and planar, then you will have the strong base come in from one side and the leaving group leave from the other side, and you will have an anti-elimination. Okay? Sometimes this is also called trans-elimination because they are on opposite sides of this C double bond C. So keep in mind, the beauty of this synthesis is not just that they're staggered, but what staggered means is there is less steric hindrance. So the base and the leaving group are very far apart from each other. No steric hindrance. Okay? As we'll see in the next slide, that could be a problem if we don't do them anti. So what happens if they're not anti? What if the hydrogen and the leaving group are on the same side? This would be called syn addition. SYN, please. SYN. Even though it's awful and ugly and bad, it's not that kind of sin. Syn addition or syn elimination. Syn elimination is still possible with these molecules. Okay? But notice what has to happen. Not only do I get my hydrogen and leaving group planar with each other, but in doing so, you have to create this eclipsed conformation. We like eclipsed. Remember, Newman projections, eclipse being good. Awful Newman projections, awful stability. So they were pulses, you can see here, and oh, this is very uncomfortable for this molecule. So really, they would never really want to do this. So the question is, why would a molecule ever go through syn elimination? Why would it ever want to go through this torture? Because typically it's not preferred. It's too much steric hindrance. The base is on the same side as the leaving group. Size, problems everywhere. So why would it ever want to do this? So typically syn eliminations do not occur unless the molecules are very rigid. Now, notice my model here of all single bonds allowed me to rotate it so I could get my hydrogen away from my leaving group. That these two could be anti to each other because they could rotate away from each other and become anti, right? So the only way that syn addition really occurs is when you can't rotate. So what can't rotate? How about this molecule? This is a ring. And so what I'd like to do is I have my models. Feel free to pause the video at any time to build whatever molecule I'm discussing so that you can follow along. And again, you don't need a fancy model kit like this one. Feel free to use toothpicks and marshmallows. I'd love to see any kind of model. You know, you can use anything you want. Sticks and dirt and mud and glue. It's like an artsy crafts project. Make your own model kit, okay? And if you do, please send me a picture of it. I'd love to see what your ring looks like with your model kit. But notice in this ring, this three-membered ring, here is the bromide, okay? And it is going down into the paper, and here's the hydrogen coming up as a wedge on this side. And again, here is the beta hydrogen. Here is a beta hydrogen. So it might be hard to see, but on all three sides, bromide, hydrogen, hydrogen, these are the beta hydrogens. Are there any beta hydrogens above the ring? No, these are all methyl, methyl. So this one is on the ring with the BR. Can't use this one. It has to be a beta hydrogen, and they're being filled by methyls over here. So what this bromide's only option is to do an elimination using one of these protons, and therefore this is going to be forced to do a syn elimination because there's no way to rotate these protons and get them anti to this bromide. Does everybody see that? Very, very rare, hard to do. Notice it's a very unique molecule to be able to get syn elimination, but it can occur. So this molecule would do syn elimination with a strong base. Here's a little overview, kind of just take-home message. I wanted to show you the syn coplanar conformation in Eclipse and compare it to the staggered coplanar anti-conformation, just to give you a sense of why this one is so much more preferred. This is what every E2 elimination is going to try to do. And keep in mind, no matter what structure I give you, you are going to want to rotate it if you can, if it's around a single bond, and rotate it until the leaving group is anti to the beta proton. Keep those two opposite each other and coplanar in the same plane. And you will be doing an E2 reaction in no time. Okay? Let's see how things can get different. And again, feel free to pause at any time. Try writing out the answer to this question before you actually run the video and see it. Okay? So, consider 1-bromo, 1,2-diphenylpropane. This is a very interesting molecule. Notice now I got lots of different groups attached to it. We are no longer in Kansas anymore, Toto. This is a weird looking little thing, but could it do E2 elimination? I have a nice strong base. That ET is an ethyl group. This is known as ethoxide. Okay? This is a very strong base. I am ready to do either E2 or SN2. I can look at my molecule and start naming the carbon that the leaving group is attached to is part of my process. Notice it's attached to 2 carbons. The pH is a phenyl ring. That's benzene. Okay? So this is abbreviation for phenyl, YL, which is known as a benzene ring. So that has a carbon it's attached to there. And there is a carbon on the other side, so this is secondary. Aliphatic, benzylic, allylic. Since it's attached to a benzene ring, it's almost on benzene. This is secondary benzylic. But you already knew that, right? You already wrote that down, right? Of course. Oh, cool. These are the 2 things you should do in your process. Write down the substrate / electrophilic carbon's first and last name, and label the nucleophile as being either a strong base or a good nucleophile weak base, or no base at all, neutral, like water. Okay? Now, what else is unique about this molecule? Well, notice there are 4 different groups attached to each of the carbons labeled there. So I should put an asterisk on each of them to remind us that these are chiral. Okay, here we go. Review, Chapter 7, helping in Chapter 8 for SN2 and then 9, E2. It's all coming together on this one slide. So if you're looking for a review, here it is. If you have 2 chiral carbons, how many total stereoisomers could this molecule have to start this reaction out with? Yep, you're right. 2 to the n, 2 squared, 4. 4 different stereoisomers. And out of those 4, 2 will be diastereomers, okay? And none of these will be meso. There is no plane of symmetry. There is no likelihood of symmetry. The 2 ends of this molecule are very, very different. If meso sounds weird to you, please go back and look at meso. And what is a meso versus a diastereomer? A good thing to stop and go back and look at the previous lectures before lecture 16. So something like lecture 15, 14, things in there, that's where we were dealing with meso. Okay? How does this play a role in our elimination story? Let's take a look. What if I looked at one diastereomer? How about this one? The RR. And definitely pause the video and confirm that these are both R. I'm not sure which way my finger is going, so let me just stop with the fingers. It's R. Each one of these should be R. Now, notice the way I've written it though. Look at where the hydrogen on the beta carbon and the bromide leaving group, how they're oriented to each other. As drawn right here, they are on the sin side, the same side, the bad side. I don't want to do my elimination with these two in the plane of the paper on the same side. So what you want to do is hold one carbon the same, like the one with the hydrogen attached to it, and take the Br, which is in the plane of the paper, and we want to move it up. Okay, and rotate that end of the molecule all the way up. And in doing so, the pH has got to come all the way around, the H has got to get pushed all the way to the back, and we end up with this rotated version now where the Br is still in the plane of the paper, but it's straight up. And if you had trouble seeing this, again, take your models, right? And here is one that I've simplified, where the red atom is the Br, okay? And the blues are the pHs, the phenyl groups, the big phenyl groups, okay? And here's that little beta hydrogen over here on the left. So I'm going to point it straight down, and the Br is pointed straight down. And notice when I do this, look at my model, the pHs are on opposite sides. One is going back away from you, one is coming out towards you. This is the wedge, this is the dotted line. Okay, does everybody see this? And so what I really wanted to do is I wanted to take this Br and rotate it all the way up. So it is now like this. It is now on top straight up, and this proton is in the bottom straight up. Looking down this Newman projection, you can see these two are now coplanar and anti to each other. And in doing so, notice what happened to the two phenols, right? They are now, if I turn it sideways again, these two blue groups are now coming out at you. They are both wedges, okay? This is really important because right now we're about to have the base come up, grab this proton and rip it off. Oh, it's not wanting to rip off. Rip off, take the bond, fold it in, and kick off. The bromide's going to take away its pair, and then, wait, maybe I just better show you. And make this new alkene bond. And when it does that, notice that the two pHs that were on the same side, both wedges here to start that elimination process, ended up being on the same side in the final product. Stereochemistry of these diastereomers matters. You might make a different product. You might not make the Z isomer, right? What if you started with the diastereomer of this molecule? What if you started with this form? I have the model of it here, but see, notice I've already drawn it beautifully with the hydrogen and the hydrogen and the bromide on opposite sides, anti to each other, and in the same plane, the plane of the paper. And in doing so, one of the phenyl groups is sticking out at you on the left-hand carbon, and on the right-hand carbon, one is far away from you. So then when you do the elimination, and make the alkene, what happens? They're on opposite sides of the chain. they will end up being on opposite sides of the alkene. And you will get E. Okay? So depending on which stereoisomer you start with, you could end up with one or two different alkenes. Depending on the stereoisomer you start with, you will end up with one of these specific alkenes, either the E or the Z. So now we have to pay attention to spying chiral carbons, spying different orientations of these chiral carbons, and then different possible products, E or Z, for your alkene. That was a lot to take in. Take a break, pause, breathe, go back and review this slide at any time. Because I'd like you to pause right now and try this problem just like you would in our class as a clicker question. Take a break. If you have to, build this model. If not, try it without the model. And I will give you 5 seconds from now before I go over the answer. So I'll start the countdown, and then you can come back and pause after the pause and see what happens. Hi again. Okay, you ready? Here we go. As you can see, the bromide is our leaving group. Beta hydrogen on the carbon next door. There is one here. There is one also out on here. This is also a beta hydrogen, but I'm going to show you in the next slide or so while that one is not as reactive. So let's pay attention to the other one. Sorry, I didn't make that clear to begin with. If we want to go play with these two, notice right now it's hard to see. Are they in the same plane? One's back, one's at you. I'd love to turn them and get them both in the same plane, anti to each other, so that we can see where the other groups are rotated. So make sure you try to rotate them. And in this case, notice I've taken the BR, that's a wedge that's coming out at you. And to get it into the plane of paper, I had to shove it down. And shoving it down, for the structure I have, I had to bring it up. Sorry. So I want the bromide to come up and be in the plane of the paper. So in rotating that end of the bond up, that takes the hydrogen that was there and pushes it back, and then whatever was back, like the CH3, has to come out now, and the CH3 is a wedge. So bromide was out. I pushed it up into the plane of the paper. That pushed the hydrogen back, and that pushed the CH3 that was back there out in front towards you. Okay? And that's how you can visualize the rotation of one end of that molecule to put the bromide in the plane of the paper. The same thing can be done on the other side. I want that beta hydrogen that's in the back up here, I want to rotate it into the plane of the paper. And I wanted to rotate it, down into the plane of the paper to make it anti. And going down takes the T-butyl group and pushes that out, and takes the methyl that was there and pushes it back. And so that's why I have the drawing before here. So now the leaving group and the beta hydrogen are in a coplanar anti-arrangement. And now you can see that when you do the elimination here with this KOH, strong base, swimming in ethanol as a solvent, just to dissolve everybody, don't worry, doesn't play a role in this because the strong base is there, and our leaving group is attached to a secondary carbon. So we have everything we need for an E2 elimination. Then that means B is the correct answer. If you got that, great. If you didn't need to rotate the bonds to get that answer, great. So the idea is just to make sure that you get the Z isomer and not the E isomer when you do this elimination. Okay? Cool. All right. If you need to take a break, this would be the spot. I didn't have a nice segue, but we're going to try something a little different. Remember that three-membered ring that wouldn't rotate? We don't see many three-membered rings, but we do see a lot of six-membered rings. Remember chairs? Woohoo! We love chairs. Yes, so it's all coming together now. If we have a chair, where's my six-membered ring? If we have this six-membered ring, remember these don't rotate very well. You cannot rotate around the bond. All you can do is make chairs that can flip. Chair flips are all we can do. So this puts some constraint on my actual leaving group and its orientation to the beta protons. So I thought this picture might do us justice. Let's look at this chlorocyclohexane in its two chair conformations. I can put that chloride equatorial, or I can put that chloride axial. I have only those two possibilities, and here they are. If you put the chloride axial, which is supposedly a bad thing, axial chloride, steric strain, okay? But notice, if I put the chloride axial, I now have it in an anti-conformation to the beta hydrogen next door, or this beta hydrogen. There's another one here. These are the equatorials. Oops, sorry. These are the equatorial hydrogens. They didn't want you to focus on those. So if I have the hydrogen and the chloride anti to each other, next to each other, because remember, axial down, axial up on the next carbon. Axial down on the next one, axial up on the next carbon. This is a perfect orientation for an E2 elimination. I can have whatever base I want here, and it can now do an E2 elimination. And I will get 100% product. Okay. This one, 100% yield of this cyclohexene. And again, the structure here is these are sp2 now. So I kind of lose the chair, but the textbook is cheating a little bit. They just didn't want to confuse you too much. But remember, that end, the cyclohexene, becomes all planar, and therefore a chair doesn't really suffice. Okay? Now, you already saw the preview of this just a second ago. Notice when I put the chloride equatorial, the Newman projection for this chair, looking down the carbon-carbon bond with the chloride leaving group, shows that the hydrogens are never anti. They are not. This axial is nowhere near planar, coplanar with the chloride leaving group. So this chloride is in a very bad position and will never, ever never form an elimination product. So what this molecule does is it's constantly ring flipping at room temperature in this reaction, and every so often it gets into the highest energy conformation with the chloride axial. So this is the highest energy conformation. This would be our lower energy conformation. So even though it's going to the higher energy conformation, it'll pop up there a little bit every so often, and as soon as it does, bam, the base hits it, does an elimination, and we get our alkene products. Does that make any sense? If not, please feel free to Zoom me, email me, come to the class. We'll figure it out. It's very cool because it's very absolute. And it's so absolute, they want to give it the longest name possible. This type of elimination that occurs on our chairs is given the name trans, because notice the Cl and the H. These two are trans to each other on this ring. I'd be looking at this wedge H and that Cl dotted line. Those two are trans to each other. They have to be in the axial position, so we call them diaxial. And anti, just to harp it in, paraplanar or coplanar. That's what this elimination is. Trans-diaxial, anti-paraplanar elimination. Let that one roll off the lips. Go talk about that one with the family. Woohoo! They love that one. All right. How we doing? Let's see how we're doing. If we had something with more than one substituent, this is again review of chairs, chapter 7. Great stuff to help us get back up to speed, but a little scary if you haven't seen it in a while. So if you recall, if we have all sorts of substituents, what position do we want all of these substituents to be? What would be the lowest energy conformation for all of these? As many as possible? Yep, equatorial. You're right. If we could get all of these substituents equatorial, that would be the lowest energy conformation for this ring. So we should start with that idea, even though we want our leaving group in the axial position. It's a good premise just to start with. So I'm going to bring up this mnemonic that we used to use to help us label these positions as axials or equatorials. And so notice, if I want this chloride, if I put this chloride equatorial, then notice the CH3, this group up here, as a dotted line, it would also be equatorial. And notice, according to this mnemonic, I go 1, 2, 3 carbons away, 1, 2, 3 carbons away, and a wedge becomes equatorial. So basically, I can draw all 3 of these substituents in this pattern in an equatorial fashion, and that would be the lowest energy conformation. So here's a picture of that. Now the reason I did that is because that's just a nice review of the lowest energy conformation. That's good to know. But is this going to be the structure that we use for our eliminations? No. I need that chloride. I need that chloride to go to its anti-conformation and its axial position. I need to do a ring flip. I need to flip this entire ring so that every equatorial becomes axial. I know that's the higher energy one, but I won't get any elimination at all unless it does this ring flip. And so all of these groups will become axial. But most importantly, you see, I will all of a sudden get my chloride axial, and then I look 1 carbon away and I start labeling the beta hydrogens. And my hope is that you find one beta hydrogen that is also axial. Straight up, straight down. They have to be trans, diaxial, paraplanar. Very strong limitations here. But then, remember, the whole reason for that is so that I can get my p orbitals parallel to one another to make a double bond. So they will do this to create 100% of this product, okay, without any other possible alkenes, because notice this beta proton, this cannot do E2 because it is equatorial to the chloride's axial. They do not have coplanar orientation to each other, okay? Only one product is formed. Kind of cool. And again, even though this is the highest energy conformation, this molecule will ring flip back and forth. And every time it ring flips to the higher energy one, just a little bit, boom, boom, E2 happens. And then I make this product, and there's ways to make sure it stays there and doesn't go back in equilibrium. A lab trick we can show you at some point. All right. Ooh, look, you guys are all jumping with excitement. Why are you all jumping with excitement? What's going on? Oh, it's because I've given you another practice problem and you can't wait to try it before our next video lecture. So this is a slightly different structure than the one we just played with. This is neomenthol chloride. Okay? So please try to draw the chair conformation that would give the highest elimination product for this. Is it the high, it might be the highest energy conformation, or it could be the lowest energy conformation. But draw the appropriate chair and then show the reaction with sodium methoxide. You can do the mechanism if you'd like. It's always cool to show the mechanism. But most importantly, show me what that final elimination product looks like. And we'll pick this up right at the beginning of our next video lecture. So please try to figure this one out and then come to our next video lecture and see how you did. Okay? All right, this has been great. I hope you've enjoyed E2 and a little stereochemical transdiaxial orientation. See you next time. Bye.